in what we've discussed so far, we've said that the first order differential equations that we've seen have a single solution that goes e to the minus kt, for example. So how do we know that there's just one solution and that there aren't more or other ones that satisfy that differential equation as well? So the answer to that really comes from what you would have studied in differential equations, but it's worth kind of talking about this so that you understand what to expect from the solutions of differential equations. So remember, everything that we're going to be doing is going to be summarized in a differential equation that has constant coefficients. And so here I've got an nth order differential equation, which simply means that the highest order derivative is n. So if it's second order derivative, that means the highest order derivative is 2, so you'd have a y double dot. And so we're going to be still talking about homogeneous equations. And so one of the key results that you would have covered in your differential equations course is the fact that this kind of differential equation has n, so if it's an nth order differential equation, it has n fundamental solutions that are linearly independent. And so that linearly independent bit is kind of important. And so that means that you cannot write one of these in terms of a linear combination of the others. And this is a generalization of the kind of linear independence that we talk about in terms of linear algebra. And so it's the same kind of idea, but generalized to functions now. But what's important is that this kind of differential equation can just have n fundamental solutions. And so in the first order case, you only have a first order derivative, and so you can only have one fundamental solutions that are linearly independent. And so one of the things that I'm going to show and it's useful on this slide, and we're going to see this repeat over and over again through this class, this particular lecture, is the fact that for these kind of nth order differential equations, they all have solutions of the form e to some parameter times t. And so this r value is what we had minus k before, but that is really crucial to shaping the way that the overall solution, what it looks like. And so we're going to talk about these. These are going to be super important for the rest of the entire course. And these we're going to talk about, starting to talk about these are the same thing as what I'm going to start talking about in terms of modes. And we're going to keep reinforcing this idea and get a little bit crisper about what modes means. But essentially the idea is that the solution, the total solution of a differential equation, can be the combination of all n of the solutions that look like this. And so why do we know that there's n? One of the ways to see that is to go ahead and substitute. So let's take one that looks like e to the rt, that's y. And so then we're going to figure out what y dot is, and what y double dot is, and what y to the n minus 1 is. And so you'll see that you just get increasing powers of r. And so when we plug all of these identities into this differential equation, they all have this exponential in common. And then you get this whole polynomial in R. And so because this is a polynomial with order n, you're going to have n solutions that allow this term right here to be 0. And the reason why we need this term to be 0 is because this exponential is never 0. So it's asymptotically goes to 0, but it's never 0. So if we really wanted it to be 0, we have to make this chunk equal to 0. And just like any quadratic, so if you had x squared plus 2x plus 5, there's two solutions that make that 0 because it's a quadratic. So the highest order polynomial here tells you how many different zeros there are of this polynomial. And so the zeros of this polynomial then end up being the entries here, the parameters here that characterize all of the n different solutions. And so just like these can be real or complex. These values here can be real and complex. And so just like we started to see in the last activity, where the sign of k really shaped the different kinds of behaviors that we see out of that system, now that the solution y, the total y solution, is the combination of all of these different yi solutions, essentially all of the different modes, And so you could have all of the modes, you could have some of the modes, you could only have one of the modes, depending on how the system is operated or what the initial conditions are. And so the key here is to understand the properties of the overall solution Y in terms of these different modes. And so that's largely what we're going to be talking about in this entire class here.